Hey everyone. In this video, I'm going to talk about random variables and probability distributions. So random variables are defined as assigning a numeric value to each event of an experiment. And remember, when we talk about experiments here, we're not talking about randomized controlled trials. We're talking about kind of the statistical idea or the idea of an experiment in statistics, which is just an event that results in a probabilistic outcome where the outcome is defined by a sample space of possible outcomes, and each of those individual elements of that sample space has a certain probability. Okay, so that's kind of the broader the conceptualization of an experiment when we think about it in terms of probability theory and statistics, not experiment in the sense of a randomized controlled trial where we assign a treatment and a control group. Okay. Um, so in this experiment, we have we assign a numeric value to each event that is part of the sample space. And the values ultimately represent mutually exclusive and exhaustive events, and together these values that the random variable can take form the entire sampling space. Okay. We can make two basic distinctions. One between different types of random variables. One is discrete random variables that take finite or at most countably finite number of distinct values, and a continuous random variable which assumes an uncountably infinite number of values. Okay, and we're going to look at two examples: one for a discrete random variable and one for a continuous random variable. So what are some examples, at least for discrete random variables? The simplest example would be a coin flip, which could be heads or tails. Those are the outcomes in the sample space, and the random variable, or kind of where the random variable ultimately comes in, is assigning now a numeric value to each event, right? So head is assigned the value 1, and tail could be assigned the value 0, for example, right? So the random variable is the assignment of this numeric value to each of those events, right? We could also think about like gambling. I take a bet. If I win, I get $100. If I lose, I have to pay $10. Or we could think about like more political events like voting. If someone turns out to vote, we assign a value of 1, and if someone does not turn out to vote, we assign the value of 0. Or in the context of survey responses, we have different types of items, Likert scales or just agreement scales. Here, one that is ranged from strongly agree to strongly disagree, and we could assign values from ranging from 1 through 4, for example, for that random variable ultimately, right? So after kind of specifying the numeric values that are kind of mapped onto the events in the sampling space, we can then characterize this random variable by specifying its probability distribution, right? And the probability distribution basically just tells us the probability of an event that a random variable takes a certain value. Okay, so for example, we could think about the probability of voting. So that means that we could compare the probability of this random variable vote being equal to 1 versus the probability of vote being equal to 0. Okay, and of course we can also think about conditional probabilities in this context. For example, the probability of voting conditional on education being held constant, or conditional on education taking a certain minimum value, and so on. Okay, so those are all kind of examples of ultimately probability distribution statements. Okay. Now, how can we characterize these probability distributions? There are two main ways of characterizing the distribution, probability distributions. One is by looking at the probability density function or probability mass function, depending on whether this is a continuous random variable or a discrete random variable. The probability density function or probability mass function basically tells us how likely it is that x takes a particular value, okay? And so for discrete random variables, this is the probability mass function, because it directly tells us the probability of this discrete event, right? So for example, we have, we could roll a die, and we could think about the probability for each number of that die, and we could directly kind of specify that probability, okay? So that's why we talk about a probability mass function, because we can directly compute the probability of individual events, okay? With continuous random variables, it's a little bit more complicated, because remember that a continuous random variable, we have basically an uncountably infinite number of events, right? It's not just one, like a die that could be somewhere between 1 and 6, but it could be, any continuous, any value on like a number scale or so on, right? The key point is that then each individual event, if you think about one specific number, ultimately has basically a probability of 0, right? Because there are infinite number of possible outcomes, because we're looking at a continuous scale. That means each individual, specific number doesn't have a probability in of itself, because there are just, uncountably infinite number of possible events, right? So we can, so that's why we talk about a probability density function. We can kind of compute a density for one specific value of x, but that density is not cannot be interpreted as a probability in of itself. We can only, with continuous random variables, compute the probability of a range of events occurring, right? So, for example, if x is some continuous random variable, the probability of x being between 0 and 1, right? That's a probability that we can compute, and we'll get in a second to how we can do that, but we can't really compute the probability of x being equal to 0, because for a continuous random variable, that probability theoretically would basically be 0, okay? Then we have the cumulative distribution function, and that ultimately tells us the probability that a random variable x takes a value equal or less than x, okay? So for the discrete random variable, we often describe this as capital F of x. That's the probability of x, the random variable, being smaller or equal to some value x, okay? And so in order to compute these probabilities, all we have to do is with a discrete random variable, we have to compute the sum of the individual probabilities of k smaller or equal to x, right? So, for example, what's the probability of rolling at least a 3 on a fair die? That's just the probability of rolling a 1 plus the probability of rolling a 2 plus the probability of rolling a 3, and so on, okay? For a continuous random variable, again, we have the probability density function for evaluated at one specific point. That probability density function doesn't give us a probability in of itself. But if we take the integral, kind of computing the area under this probability density function for a specific interval, then that area ultimately will give us the probability of this continuous random variable taking the range of values, okay? So the probability of x smaller or equal to x is equal to the integral up to that point x, okay? So we're looking at the area under the curve up to that point of the probability density function to compute the cumulative distribution function, okay? In addition to kind of specifying the probability density function and the cumulative distribution function, there are a couple of key characteristics of probability distributions that we usually think about and that we use to characterize those distribution functions. The first one that we talked about at length before is the expectation. The expected value of a random variable x, or e of x, is again for discrete random variables just the sum of x times f of x. So we're basically multiplying each value of x times the probability of x, which is here f of x, and we sum all of those together. So this is kind of just, you know, the weighted sum, where each value of the outcome is weighted by the probability of that outcome occurring, right? If x is continuous, again, since we have a continuous random variable, we cannot sum individual probabilities that are weighted. We have to take the integral of our probability density function and kind of in an analog in the analog kind of way. We multiply x times f of x and take the integral with respect to x over the entire range of x, so to speak. Okay. An example, and I kind of mentioned this already, if we want to compute the expected value of a fair die, we just take each value that the die can take times the probability, that's 1 over 6, and we sum those all together, and so that's 7 over 2, so that's 3.5. Or if we have a sample of 3 rows, that would just be the sample mean of 3 rows, 3 throws of that die, that would be just, 3 in this example. So there's a difference between, the only point here is that there is a difference between the sample mean and the expected value of the random variable itself, right? The sample mean is based on some realization, some data that we observe. The expected value kind of summarizes all possible values and the underlying probabilities, okay? We also have to keep in mind that the expectation is the linear operator, and by virtue of being a linear operator, it has a couple of properties. For example, the expectation of some constant is just equal to the constant. The expectation of a constant times a random variable x is a times the expectation of x, so we can just pull out any constant in front of the expectation. If we have a random variable a times x plus b, so again plus a constant b, we can also pull out the sum, so that's a times the expectation of x plus b. If we have 2 random variables, x and y, and we have the sum of those 2 random variables, the expectation of that sum is the sum of the expectations. And in addition, if x and y are independent, then the expectation of x times y, so the product of both random variables, is equal to the product of the expectations. But that only holds if x and y are independent. If they're not independent, then we have to take into account the covariance of x and y. Okay. Just a second. Okay. In addition to expectation, another measure summarizing probability distributions is variance, or variance and standard deviation. The variance of x is, of course, the expectation of the deviation between x and the expectation of x squared. Okay. And we can simplify this a little bit further if we multiply out this square, and then simplify a little bit. We have x squared minus 2x expectation of x plus ex squared. That's just this square multiplied out. Note here that we can kind of pull out these expectations, write them separately. So we have ex, the expectation of x squared, minus 2 times the expectation of x times the expectation of x. Of course, this turns into 2 times expectation of x squared plus the expectation of x squared. That's this last component. And that can be further simplified into the expectation of x squared minus the expectation of x squared. So on the one hand, we have the square of the expectation, and on the other hand we have the expectation of the random variable squared. Okay, that's the big important difference here. Okay. The standard deviation of a random variable is, of course, the square root of the variance. And again, we have a couple of properties of this variance and standard deviation. First, the variance of any constant is equal to 0. That makes sense. The variance of a constant times a random variable is a square times the variance of x. So we can pull out the constant, but if we kind of go through, we could kind of show this by using this definition of the expectation of the variance and plugging this in. And we have to take into account the square when we pull out any constant. The variance of x plus b, since we're just adding a constant and the variance of that constant is equal to 0, that just turns out to be the variance of x. And kind of both rules combined, if we have the variance of ax plus b, that's just equal to the variance of a squared plus is equal to a squared times the variance of x. Okay. Then if x and y are independent, then the variance of x and y is equal to the variance of x plus the variance of y. Again, this only holds when x and y are independent. And then related to variance and standard deviation, we also have the covariance and correlation that we talked a bunch about last semester. The covariance is, of course, can be described as the expectation of x minus ex times y minus ey, and we talked about kind of how to interpret kind of the sign of the covariance in that context. We can also multiply this out and then kind of write this as the expectation of x times y minus the expectation of x times the expectation of y. That's a common kind of simplification of this term, and then again, compared to the covariance, which is not on the same scale, which is kind of hard to interpret because it basically the scale of the covariance depends on the scaling of x and y. What we do is we compute the correlation, which is just the covariance divided by the square root of the product of the variances of x and y. And what this does is it ultimately rescales the covariance in such a way that the correlation is now ranging between -1 and 1 for perfect linear relationship, perfect negative linear relationship for -1 and +1 for perfect positive linear relationship. Okay, so much about our review of variance and covariance, as well as the expectation. In the next video, I'm going to continue with 2 examples, one for a discrete random variable and then the second one for a continuous random variable.